Welcome to Data Skeptic. Data Skeptic brings you discussions about how data is changing our world. Our interviews are conversations with thought leaders in topics like data science, machine learning, and artificial intelligence.
Ramya Ramakrishnan is a PhD student at MIT in the Interactive Robotics Group. Her research interests include reinforcement learning, interactive machine learning, and human-robot interaction. Ramya is excited about developing AI systems that can be safely deployed in the open world through human feedback. I invited her on the show to talk about the recent paper, Discovering Blind Spots in Reinforcement Learning, which she authored with co-authors A.J. Kumar, Debadipta Dey, Julie Shah, and Eric Horowitz. Well, Ramya, welcome to the show.
Hi, Kyle. Nice to be here.
Yeah, it's a pleasure to have you. So I really enjoyed reading your recent paper, Discovering Blind Spots in Reinforcement Learning. To my read of most literature, the idea of a blind spot isn't there in necessarily all of machine learning and reinforcement learning. Could you tell me what the idea of a blind spot is?
Sure. So blind spots are unexpected errors that a machine or agent makes because its training environment is different from the real world. So a lot of AI systems get deployed into the real world, and they're making a lot of these mistakes because it never saw it during trainings. These are really, really difficult errors to catch, but it's very important that we look out for them.
I like that the work is calling what you're studying a blind spot. I think it is an appropriate name for the kind of direction you're going in improving machine learning. But it could be compared in contrast to a number of existing terminologies, right? We could say that, oh, this is a form of transfer learning, like I was talking about earlier, or it's a form of anomaly detection. Could you compare and contrast a little bit with things you might call it and why blind spot really is a distinctive approach?
I think a lot of those areas are definitely related and relevant. In our approach, we are sort of assuming that your state representation is sort of incomplete. And when your state representation is incomplete, it's very difficult to use some of these approaches because you don't have the full set of features to really make a prediction.
So one famous example that involves reinforcement learning is, of course, AlphaGo or AlphaZero, now the new iteration. And that used a simulator, but it doesn't really matter, right? The simulator perfectly captures the state of the game Go. What are examples of a case where the simulated data wouldn't match the real-world application?
I think autonomous driving is a really important application nowadays where cars are being deployed into the real world. And if your simulator doesn't have, for example, police cars, ambulance cars, fire trucks, right? You go out into the real world, you've never seen these cars in your training, and you don't know how to react to them. You could also think about in medicine, there's blind spots in that application as well, where doctors can't see the full state of a patient's health. And so you have to make decisions without sort of knowing what what their health is actually like.
I like the idea of the blind spot a lot, and I think it contributes well to how we should think about development of machine learning. But I want to explore maybe the analogy towards a human blind spot. When I think of that, I'm aware that there's something about the design of the eye where my retina doesn't quite see everything and my mind kind of fills in the blanks for me.
Mhm.
Do you think the analogy holds up under that level of scrutiny, or is machine blind spots fundamentally different from biological blind spots?
I think that they're comparable in the sense that there are limitations in human sensors and there are limitations in agent sensors, and that causes sort of certain regions of the space to not be seen or not be understood. In the case of human blind spots, I think, well, I guess it depends on how you think about blind spots, but in the car example, there's a region behind your car where you can't really see cars coming up next to you. And people know that that's a blind spot, but people have learned to deal with that by being very, very careful, having a rear view mirror, adding sensors that the eye doesn't actually give you in order to deal with that sort of blind spot. But I think there are still blind spots in the world. Again, with the doctor's example, doctors are making decisions based on what they see, but sometimes two patients look identical and you make a decision that's sort of incorrect, and that can really affect the patient.
Another aspect of this is maybe we could try and get rid of the blind spots by providing more robust training data. I've seen some papers where in the self-driving car example, they're trying to go through and repaint different scenery and put like snow onto the streets and stuff so that the simulator would have more example data where that's atypical. Do you think that's one front of the battle against blind spots, or is that kind of a losing front? Are we ultimately not going to be able to try and fill in the missing places in our simulated examples?
I think that's definitely a great area to explore because the more robust we can make the agent during training, the fewer errors it might make in the real world. So I think that definitely needs to happen to make that training more realistic. But I think regardless of how much you try to make this simulator as real as possible, there's still going to be a gap. So I think it's important to also address this transfer from simulation to real world, regardless of how good the simulator is.
So I guess we're kind of starting from this assumption of, hey, there are going to be blind spots. So rather than, or fill them in where we can, but acknowledge that we can't fill them all in, can we learn to recognize them?
Yeah.
Is that sort of the core thesis you guys are working on?
Yeah, exactly.
Yeah, very neat idea. Let's dig right into it. Can you tell me a little bit about the approach?
So blind spots can come from a whole variety of reasons. And the blind spots that we really look at is blind spots due to limited state representation. So what that means is the agent has missing features and it goes out into the real world and it sees many things as the same. Take the example of a fire truck, right? So it sees a fire truck and a car exactly the same. And it actually should be acting very differently towards them, but it can't because it just can't see that they are two different things. Learning these sorts of blind spots by itself is very, very difficult. Our approach is really thinking about how we can use human feedback or oracle feedback to learn these blind spot regions. And intuitively, what we are doing is we are sort of getting signals from the person. So for example, if the person is doing two very different things in a state that I'm seeing as the same, that might be an indication to me that I am doing something wrong or, things like that. So really using that human feedback to try to figure out maybe blind spots that I might have.
Yeah, so tell me a little bit about that pipeline.
Sure. So the input to our pipeline is the learn policy that the agent has from a simulator environment, access to an oracle that can provide feedback in the real world environment, and some budget that limits the data that the agent can get. And the output of our pipeline is a blind spot map that tells the agent how likely each state in the agent's representation is a blind spot. And this model can be really useful because in the real world, the agent can then query a human for help if it thinks a state is likely a blind spot. And so with this input and output, we then have a pipeline that consists of three different parts. So the first part is a data collection phase where the agent is getting data from an oracle or a person in the real world. The form of the feedback can vary, but ultimately the type of signals that the agent is getting from the person is whether the agent's action is acceptable or not. Now, the issue is that because the agent's representation is limited, it sees many real-world states as the same. And so it's going to be getting many different signals for one specific state. And so that leads us to the next part of our pipeline, which is aggregation of different signals. So if the agent is getting many signals for a state, the agent needs to aggregate all of this information in order to estimate whether each state is a blind spot or is it safe for me. And the output of this aggregation is how likely each state is a blind spot along with some confidence. How sure am I that this is a blind spot based on the signals that I've gotten from the person? And then finally, in order to generalize this information to unseen states, because we're assuming we have limited budget, and so we can only estimate for the visited simulation states with this aggregation approach. But to generalize to new states, we then perform supervised learning to predict how likely any simulation state is a blind spot. And this gives us this output blind spot model that we've been trying to get.
What are the different forms of data collection you're using?
So in the first part of the pipeline, I talked about data collection and that there were different forms of feedback. So there's actually two forms of data collection that we look at. One is demonstrations and one is corrections. And so demonstrations is when the human performs demonstrations of the task in the real world. And corrections is when the human monitors the agent and corrects the agent if it does something incorrectly in the world. And both of these are safe forms of getting feedback in the world, which is really nice.
It was an interesting path for me. I did not come from computer science. I was working in the environmental field as an environmental scientist for 5 years. I started to get to a point where to progress further in what I found interesting, I had to learn how to code.
Thanks to this week's sponsor, Galvanize. You're hearing from Zach Estella. He's an alumni of their data science program.
And so I started teaching myself Python and took this windy path of getting this repertoire of skills, but not having the credentials on paper or comprehensiveness to get a data science job that I was looking for. And I decided, okay, I'm going to go all in. I'm going to do Galvanize. I'm going to get all of my skills, get connections, and meet cool people. All of those things are what I was hoping to get when I started, and that is what I got. It was great.
Galvanize has a 13-week full-time immersive program that teaches students Python, statistics, machine learning, and all the tools you'll need to have a successful career in data science.
It was really intense. You get 10 hours a day. There's lectures that are really finely tuned, interspersed with computer time. So if you're a hands-on thinker, you can just dive right into doing it. And for me, that was really nice.
Get taught by industry veteran data scientists who will not only teach you the fundamentals, but build up the skills you'll need to make a capstone project.
So I built a fake news detector that tries to find bias in the media, and it uses a lot of cloud computing, a lot of AWS. And so just dipping my toes into that and realizing to at least jump in and start breaking things or making things, it just opened this whole world to me.
Graduates from the Galvanize program go on to work at Accenture, Facebook, PayPal, Lyft, GE, Salesforce, IBM, Apple, Amazon, American Express, and countless other everyday names.
If I could have just traveled forward in time and do Galvanize, that would have just fast-forwarded me so much.
Find out if the Galvanize program is right for you by visiting galvanize.com/data-skeptic. One more time, that URL is galvanize.com/data-skeptic. Interesting. So yeah, we've got two methods of feedback here. Can you talk a little bit about how effective each were?
So I think each of them has its pros and cons. So demonstrations is usually a little bit more easier to obtain, and corrections, it requires a person to actually monitor the agent. And so usually it's a little bit more expensive. But corrections can give you data directly on the states that actually matter to the agent, because it's the states that the agent is actually visiting in the real world. Versus demonstrations, if you assume that the person is doing the optimal thing, it's only going to see these optimal set of states. So what we saw in our results is that corrections does really well. You can actually learn these blind spots according to which states you visited. In demonstrations, it depends. If you look at demonstrations and you consider every mismatch with the person as sort of a blind spot, then you end up having a really conservative agent. So this agent, like anytime I deviated from the person, I'm just going to sort of move away from that region. And that actually turns to work out pretty well, because the agent sort of learns to altogether avoid blind spots because it's being super conservative. There are cases with demonstrations where if you recognize those states to be safe, you can venture into sort of unknown territory, because demonstrations is seeing sort of a whole different part of your state space than is actually important to you.
I see the value in both, and I think, going project by project, I might have to select very carefully which one's more appropriate for me. Let's say I have a project I'm trying to solve. Maybe I'm teaching a robot to play golf or something like that.
Mm-hmm.
Give it some feedback through some reinforcement learned simulator. After all, golf is just basic physics. Should be pretty easy to show it, computer golf. But then I want that robot to play in the real world. And there'll be occasions when maybe it'll do something that doesn't align with the human behavior. So I've got to give it the examples of how the human hit it, essentially, I presume, right? Or maybe I know in advance that there are tricky things one has to learn about golf. So I set up a course that exemplifies that tricky thing and I show it the human shot. So I have these two kind of neat approaches. Does my choice in how I train the robot maybe introduce any bias? Like if I focus too much on demonstration, will I create an agent that is overly conservative and not generalizable? Or are there any considerations like that you discovered or thought about as working through it?
When you look at this correction data where the agent is actually being monitored by the person, the types of states that you're visiting are the states that the agent actually visits. It's the sort of most important states for the agent. When you look at demonstrations, you're getting bias based on the states that the person is visiting. And usually this is based on sort of the optimal behavior of how you would act in the world. And sometimes that actually is very different from what the agent is doing. And so you might learn that the person is going into this completely different region. And maybe to me, I see that as, I'm deviating from the person. I'm going to actually not go into that region. And you might actually become overly conservative.
So on the show recently, we've talked a little bit about transfer learning. You can train one system in one domain, let's say image recognition, train it on a big class of images, and then retrain it a little bit, take parts of the original network and extend it to train in your specific application. I like the example you were giving of a self-driving car, that maybe it's learned all these simulator things, but it doesn't know to recognize an ambulance. So the first time that self-driving car is pulling down the road, it just sees a random vehicle, not an important vehicle you have to pull to the right for. And that would be an example of something outside of its training data. But I also worry that if we've already trained the deep learning part of the system to recognize parts of that image, then maybe it hasn't learned how to recognize the important shapes that would allow it to learn what an ambulance is. What if we train on simulated data and we find a model that's capable of learning the simulated data, but missed out on learning some more fundamental thing that would allow it to get the benefit out of the corrections and demonstrations? Can you talk about maybe the deep implementation, whether or not that's a concern, or if we go and retrain at a more fundamental way?
Yeah, I definitely think that this is a big problem when you consider deep learning systems. I think it makes it much harder because you don't really know, what features it's learning. You don't really know what's going on inside. I think there's definitely blind spots when you think about implementing these systems in deep networks. I think that you can sort of still use this sort of pipeline of trying to use external feedback to learn these blind spot regions. I think it makes it even more important in deep learning scenarios because of the sort of less interpretability that you get. Getting human input, comparing with the actions that you would take, estimating blind spots based on that, I think is going to be still valuable when you think about deep learning systems.
Absolutely. My next question is going to vary from different application to application. When we were talking earlier about a mini golf playing robot, it's not the end of the world if it fails to do a good job, but a self-driving car, the stakes are very high. How do you know how much of the blind spot training to do? I imagine there's a cost to it, right? Giving demonstrations or having a human correct an example, it's a slow and laborious and expensive process. Can you account for that in the way you guys approach the problem?
I think you're absolutely right that data is really difficult to get, and it's hard to know, how much data you need to learn these blind spots. I mean, we look at how the effect of the algorithm is as we vary the budget, or basically the amount of data that we get. And of course, the results are better when you have more data. But I think one thing that we sort of need to think about in future work is trying to maybe do more intelligent data collection. So if an agent can actually query for data actively, that can potentially make the data process a lot more intelligent, and you can learn from much less data than we are currently.
Interesting. And do you see that query process being sort of a real-time system, or is it in batch mode that it'll kick out some examples and say, hey, I didn't understand these. Can you help with this selected few?
I think it could definitely be both. In the batch case, you could definitely learn a lot from learning before actually going out into the real world, but also updating your model as you go, right? Because I think that's how humans do it. Humans are constantly learning and constantly updating their model of what they know or what they don't know. So I think that is really important as well.
I know this is a bit of an abstract question, but I'm just curious if you've encountered it since you've been looking into this. In those cases when a machine learning model is making mistakes or its behavior is differing from what a human would have chosen, in what way is the behavior differing? Is it that it gets to this new scenario that it doesn't know how to handle and it just starts going wacky and executing actions seemingly random? Or is there a sort of a logic to it? Like, would we observe it and say, oh, you made a silly mistake?
So the error that the agent makes, at least in the domains that we considered, the error is because the agent is sort of missing a feature. So a person might be able to sort of tell that, okay, maybe for example, in the automated driving scenario, if the agent sees an ambulance and sees a car and keeps driving in both scenarios, the person might say, oh, well, maybe the agent isn't seeing the ambulance. But I think it's not always so clear, right? Because every state that you see in the world, there's so many different factors that are affecting your decision. So I think it's not always intuitive why the agent is making that error. But given that we are sort of constructing the scenario for this work, we can sort of see that, okay, the agent is making these errors because this specific feature is missing.
And I think we touched on this a little bit earlier, but now that we've gotten kind of into more of the details, could you remind us of some of the feedback types you use? And then let's get into a little bit about the improvements that you saw empirically.
So we considered some feedbacks that were sort of like random baselines. It's just nice to think about how these approaches work when you don't have the bias and correlated data. So we have random data where the states are sort of randomly sampled in the real world. It's like a person just handpicked some states. And then we have demonstrations and corrections. Within demonstrations, we considered two types of demonstrations. One where all you see is demonstrations in the real world. You don't get to talk to the person after that. You just sort of see where your behavior matches and where your behavior doesn't match. And then in the other demonstration case, you see those demonstrations, but after that, you are sort of able to query the person and ask about all of the cases where you mismatched with the person and say, hey, like I did this thing, you did this. Am I doing sort of something unacceptable or am I doing something equally good? And so you're getting more information in the second demonstrations case, but it also requires more input from the person.
Well, one of the important themes of the paper, and something we haven't touched on yet, is the element of noise. Maybe the agent makes a mistake because they got a faulty sensor reading, or maybe they made a mistake because they didn't know how to understand the sensor reading. How do you distinguish between the two?
Yeah, so we have different forms of noise in this problem. One type of noise that we get is state representation noise. And this noise occurs because the agent and human are acting in very different representations. The agent is seeing many real world states as identical, and it's getting, because of that, contradictory or noisy signals from the person. So, for example, if the agent sees a flashing light police car and a regular car as identical, it might get two very different labels from the person. One where the person is saying that the agent should slow down, and another where the agent is doing exactly as it should and just driving behind the car. And so these two labels are actually assigned to the same state, and the agent has to deal with this kind of noisy feedback. One thing to notice here is that if the agent is getting many safe labels for a state, it can't confidently assume that the state is safe because there might be another state that looks just like it where the agent is not acting properly.
Yeah, can we go in a bit to the reasoning side of thing? Is it a Bayesian approach, or how do you implement uncertainty?
The way that we look at this problem is we say that for each of these states that the agent can see in its simulator world, it's getting these multiple signals from the person that's noisy. So we actually use an approach that comes from crowdsourcing, where you get many noisy labels for an example, and how do you actually deal with that? So we use an EM style, expectation maximization style approach, where we learn the prior distribution of the data, so the ratio of blind spots and safe states, and also a confusion matrix, which is basically the noise model between observations and true labels. So observations meaning, am I getting a signal from the person that something is a blind spot or not? And then the true labels, which is the blind spot states and the safe states. So we're learning this confusion matrix and the prior iteratively, and then this gives us an estimated aggregated label for each state.
And it seems like there's a couple of sources of noise then in the system, right? What else might the agent need to deal with?
The first form of noise assumed that the agent was getting direct feedback on its own actions. But what if the person never told the agent whether the agent was doing something acceptable or not? So the second form of noise that we get is called action mismatch noise. So far we've assumed that the oracle is actually giving feedback directly on the action that the agent is taking. But another way that you could collect data is the agent is just simply observing an oracle or a person demonstrating the task. And so if the oracle takes a specific action and the agent takes a different action, this could be indicative of a blind spot because the agent is not following the optimal action. But two actions could be both acceptable in a state. So a mismatch doesn't necessarily imply that a state is a blind spot. So this is really where you get that action mismatch noise. And the agent has to deal with that kind of noise when it's learning.
Interesting, yeah. When we think about, video as the source or images as the source, yes, deep learning kind of does some automated feature recognition, but at the lowest levels, the features are the color values of the pixels. I presume you don't mean that it's missing some particular pixel value, right? Are you talking about the more abstract idea of a feature in that case?
Yep. So maybe it's seeing these colors, but it doesn't actually detect at the sort of very highest level. It's not detecting an ambulance, even though it could maybe detect it from the pixel values, but it just didn't learn those intermediate features to be able to recognize one.
So I see a lot of potential in the methods to help us gain some confidence that our systems are safe and robust and that sort of thing. We want to Maybe before we put a self-driving car on the road, put it in a fake little closed course and have an ambulance drive past it, make sure it reacts in the way we want. And this can be a technique to help kind of ensure that we've given it all of the example cases we want to cover. Do you think this ties in at all with coming up with a metric that we've shown enough examples to something we can certify it as being robust? Or will there always be this worry that that innumerable state space contains some mystery that the machines have failed to learn?
I think there's always this sort of mystery that there are things that you're missing. I think having these approaches sort of bridge that gap a little bit. It reduces that gap and tries to make it more and more realistic. But I think that developing algorithms so that systems can be sort of always monitored in the real world, I think is important, because not only is the real world different from maybe simulation, but the real world is also changing. So I think it's really important to adapt to what the real world data is. And that's going to involve continuously monitoring the system and continuously seeing if the system is making errors and updating based on that.
To wrap up, I'd love to ask you a little bit about where things are headed next. A paper obviously is available. Well, first, is there anywhere it's going to be published next?
This paper is going to be presented at Autonomous Agents and Multi-Agent Systems, which is coming up in just about a month. And if you're there, I'd love to talk to you about the work.
And what happens next after this? Was this kind of the pinnacle of a long line of research, or is this the start of a whole new direction?
I think it's the start of a whole new direction. I think it's an exciting area, and I hope that other people join in and really think about this problem. I think it's a very important problem. So there's a lot of interesting ideas for future work. As I mentioned earlier, the agent currently is getting a batch amount of data, but I think it's really important to think about an agent that's querying in the world and getting data in a more intelligent way, because one, getting data in the real world is expensive, and also putting a human in the loop during this data collection is also expensive. So that is a very important area to look into. I think also we've just discovered blind spots. And so I think there's a lot that can be done in terms of fixing blind spots, maybe adding in missing features. Maybe you have new sensors and you want to sort of reason about how you can add this back into your representation. Maybe humans can be involved to provide features that you're missing. And then also right now we've been considering a very perfect scenario, right? You have infinite training time, you have a perfect person giving you feedback, but really in the real world, you're having people giving very noisy demonstrations. You're probably going to have limited time in your simulation to train. So how do you deal with some of the errors that you're getting from other aspects that you're really not considering right now? I think that's important as well, thinking about a more realistic scenario with more noise coming from a whole lot of other factors.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.